Welcome to Exploit Research Megaprimer Part 3. In this video, we will look at how to inspect and exploit an strcpy based buffer overflow. Please view the previous set of videos if you haven't already done so, because basically we are building on a lot of knowledge and a lot of things which we've already looked at in the previous videos. So now in this video, the vulnerable function is actually going to take user input and going to call the strcpy function to copy user input into a buffer, and this buffer is of size 256 bytes. Now, as you probably already can imagine, if the size of input is going to be larger than 256, then it is going to go ahead and write further ahead than the bound of this buffer and hence cause a buffer overflow. So before we get into the next slide, let's analyze this program and this demonstration. So what we'll do is we'll once again very quickly first look at our source code for this program. So I'm using the exact same program as in the last demonstration, but there's a little difference, and that little difference is instead of memcopy, what we basically have is strcpy, which of course does not take the size, maximum size as input, and this is how the function currently looks like. And once we've compiled the code, you basically have the server-strcpy.exe executable. Now this executable is available for download from the same page, so please do that and follow this video. Now this executable is a simple echo server. What does it do? Well, let's open up our PuTTY terminal in which we are logged into Backtrack. I think the first thing is to first figure out our IP address, which is 192.168.1.2. So let's actually do a netcat to port number 10,000, which is where the service is actually listening. We are connected, and now anything we type in hi, the server responds back with a identical response, and this is what we call an echo server because it echoes back whatever we type in. So we can actually type in hi there, hello, so on and so forth, and once we exit, the server exits as well, right? So what we are trying to do is exploit a buffer overflow in this server. So the first thing we need to do is first figure out if there is a buffer overflow. So let's quickly create a program which can interface with this executable. So I think what I'm typing in right now should be familiar. This is exactly what we did in the previous video. Then we go ahead and connect to the remote socket, give it the IP address which we'll take from user input, and the port number which we can hard code as 10,000. Then we send in a buffer which is identical to what we did in the last case. All A is 2000 times. We send the buffer across and then we close the socket, right? Let's change permission so that we can make this an executable. And now let's go ahead and execute it with the remote server's address, which is 1.2. So we've run it, and now if we go to the remote server, there's been a crash, and let's click on the detailed report, and you would notice that all 41s are currently here. So the EIP has been overwritten with our capital A, because 41 is the ASCII value of capital A, as we've discussed in the previous video. So let's go ahead and now analyze the situation a little bit better. We'll open up Immunity Debugger and load this file through Immunity. So this is the disassembled version of the executable. Let's go ahead and run the program. Program is now running. It's listening to the socket 10,000. Now let me fire up the exploit program again, and as expected there is an error, and the good news is EIP has been overwritten. Now this is verified. Also ESP, which points to the top of the stack, is pointing to our data which we sent in the form of allays. Awesome. So this is a classic vanilla buffer overflow exploit, and now we'll go about quickly analyzing this as we did in the previous case. Right? So the first thing is to restart the program. And now if you remember, just like in the previous case, the whole idea is to send a pattern using the Metasploit tool. So for some reason this terminal is hung. Let me open up a new terminal. Okay, I think it just got recovered. So we'll go to the Metasploit directory, which is located in pentest exploits framework 3, and then inside that the tools directory, and we'll go ahead and run the pattern underscore create tool, the pattern of 2000 characters. So this has given us the input. Right? If you're confused at this point, I'm very sure you haven't watched the previous video. So go back and watch the previous video. I've already given explanations of why we are generating the pattern and all of that in sufficient depth in that video. So let's copy paste the pattern, and now let's run the exploit once again. The server is running and listening. Right, the exploit went through and the server has crashed as expected. And if you can see, I mean, most of the data is identical to as in the previous example, but we can go ahead and verify it once again. So the first thing to figure out is the offset of EIP, right, and that we can figure out by the value currently within EIP. So we will quickly use the pattern underscore offset utility and give it the input which EIP has within itself, 41, 39, 69, 268, just like in the previous case. And then top of the stack ESP is currently pointing to this pattern 0AJ1. So we have 0AJ1 and this is 272. Awesome. So I guess this is exactly what the scenario was in the previous case. Now let's analyze this further. Now what we're going to of course do is first verify the exact offsets of EIP overwrite and ESP overwrite. So we know that first we can send 268 bytes of garbage. After that we are going to do the EIP overwrite. Right, the time being, let's say this is all B's. Then we are actually going to do a ESP overwrite, which can be all C's, and then we can actually go ahead and fill the rest of the things up with all A's as before. Right? Awesome. So now let's quickly send this to verify that the positions that we've calculated are working perfectly. So let's restart the program, run the program, go back here, run our exploit code, and perfect. EIP has been overwritten by all B's, and ESP top of the stack has been overwritten with the first 4 C's, and then we have all the A's. And if you can now scroll up, well, this is exactly the place where EIP is being overwritten, and this is the place where ESP is pointing to just after the function returns. So like in the previous case, what we need to do is we need to overwrite BBBB with a return address pointing back to the stack, right? And just like in the previous case, it can be the top of the stack. Now let's go ahead and actually do this, but what we will see is there are a couple of differences now because we are using strcopy, right? Anyway, so the current location of ESP is 0022FB70, right? Awesome. Let's go ahead and hard code that here. So let me write the reverse value of ESP. It's going to be 70 FB 2200, right? And at this point we are going to insert our shell code. So for that, of course, we're going to have to generate our shell code. And I think if you remember from the previous video, the first thing is to figure out which payload we want to use. We'll use the same payload as previously, which is going to launch a remote root shell on the system. So let's quickly wait for MSF payload to run. Awesome. So let's just take up the bind TCP, which is the exact same one as in the previous case. So we have MSF payload and we want the output in a CRA format. Right, we just go with the default options. We'll go back to our little script here and copy paste this value. We are ready to hit the experiment once again. Let's just quickly restart the program. And let's run our code. Now what you would notice is the program has crashed once again, but it's not working as expected, right? This is a bit worrisome. Let's try and understand what just happened. So let's look at the stack, because that is where we try to overwrite everything. Let's basically go ahead and follow it in dump this time. So this is the top of the stack. Okay, so if you notice, all the capital A's, basically if you try to map it with what we've sent right now, we first sent 268 A's, right? And this looks like this is the whole A dump, right? It's kind of coming down here and it is stopping at a point, after which, if you kind of remember our original program, we've kind of overwritten it with 0022 FB70, and this is exactly what we are seeing in reverse order, 0022 FB and 70. Now after that we have our shell code, which is basically FCE8, 89 and all of that. But if you notice, for some reason after 0, which is where we overrode the return value, well, the rest of the characters don't really match, right? We have tons of zeros and all of that and whatnot. So what happened? So this brings us to the discussion of bad characters. So let's quickly come back to the presentation to understand what this means. Now, bad characters basically are characters which are used to delimit input from the user. So what is the input we send to the program? That long string. Now, that long string was using the strcopy function to actually copy user input into the array, which we overflowed. Now the problem really is that the 0x00 character is actually a null byte, and at that point strcopy thinks that basically the string has ended, and hence what is happening is the moment strcopy is encountering this value 0x00, which is the address of the top of the stack, part of the address, it actually terminates the string here entirely and doesn't even consider the rest of our input. So what happened is the only thing stored on the stack was just this. The rest of this was not stored at all. Right? Hence all our shellcode and anything after that just got discarded. So this is a problem, in which case what we figured out is 0x00 is actually the bad character. Now, how do we verify this? Well, the whole idea behind verification of bad characters is in the next slide. Now what we need to do is we need to send the program the full list of characters ranging from 0x00 to 0xff, and then using a debugger just like we did right now, we need to figure out if input breaks. If so, then we find the character which breaks it, and then we remove that character from the list and then go again back to point 1, and now with that reduced set of characters we again run the same experiment. Now at one point what we would notice is that input no longer breaks, which means that the rest of the characters can be used safely. So now let's try and do this in a practical way. So let's restart the program. Now we need to generate the whole list of characters from 0x00 to 0xff. So for that, you could use other utilities as well, but I've just created a very simple program, not this one. It's called chargen.c, and all it is doing is basically running a counter C from 0 and running it till 255 and basically printing the value in hex format. That's all this is doing. Right? So if I kind of go ahead and run this program, it will go ahead and dump the entire list of characters in incremental order, 0x00, 0x01, 02, so on and so forth till 0xfe. Now what we need to do is I just need to copy this and then go back to my old program, and let's just quickly remove the shellcode because we really don't know what are the bad characters in this. And after the A's, let me just go ahead and paste this entire set of characters, and then post that I can actually paste a couple of A's once again, so that I know that the whole character set was actually covered. So at some point we'll know that after FF, if once again A start, then all the characters here are allowed and not bad characters which may break input. Right? So having done this, let's go back. The program has started and it's running. Let me hit this once again. Sending the input to the remote program. And here we again had a crash. Let's just follow the stack in the dump. Now if you kind of go up, what we would notice is that after our A's, which ends here, the first character we sent was 0x00. If you kind of remember how this looks like, right? We sent 268 A's and the first thing we sent after that was 0x00. Now after 0x00, if you notice, we have something different, 1640 whatnot. Ideally here we should have had 01, here we should have 02, 03, and that should just have continued. So 00 is definitely a bad character because after that any input which we sent to the program was discarded. So 00 is a delimiter. Now note, this is probably obvious because we also know the source code of the program using strcopy, and we know that strcopy would use the null byte, which is basically just a 0, as a delimiter. But even if we did not know what function was being used to actually copy our input into that small buffer, this technique would tell us what are the bad characters. So now let's go ahead, restart the program. And we know that 0x00 is actually a bad character. So let's go ahead and remove it from our list. And now we will send the rest of the characters. Everything is sent, and there is another crash right now, but what we need to inspect is how the stack looks like. Okay, awesome. So after 41 we have 01, which is the first character we send, then 02, 03, 04, and that is now continuing. What we need to see is if this ends with FF, and after that basically at 41 start again. Awesome. So FF in the incremental order of what we had, everything is on the stack right now, and after that we have our 41s, right, which is the pattern which we had sent. So this is exactly what we sent. We first have our 41s, which is all capital A, then we have 01 to FF, and then we finally have again the A's which were appended, and this is exactly what this is showing. So now we know that in our input 0x00 is a bad character which cannot appear anywhere in our shellcode. So let's go ahead, restart the program. Now there are basically two challenges. If you notice in the previous case, what did we do? Let's kind of go back to our presentation to get some idea. So in the previous case, we basically had the value of ESP, which was basically 0022 FB70 when it was actually crashing, not this value, and we basically ensured that after the returning, EIP is going to point here and we're going to continue execution. So basically we were overwriting the return value with the value of ESP, but here's a problem. The address ESP actually contains a 0. Now the problem is because one of the bytes of the address is 0, if we overwrite the return address with the address of ESP, then basically this won't work because the 0 is actually a bad character which will go ahead and delimit the input as we just saw. So what that means is that this technique currently cannot work by simply using ESP as the return address. So what are we going to do? Well, the whole idea is going to be that instead of using ESP as the return address, we're going to have some other return address, and that return address is actually going to point to a piece of code, basically somewhere probably in any DLL or probably anywhere even in the program's code, which actually has a jump ESP statement in it. So let's say MNXYABCD is basically that address which we're going to overwrite, which does not contain any zeros in it. So when the function returns, EIP is going to go ahead and point to MNXYABCD, which probably is some location in the program space, either in the program's own code or any of the DLLs it is importing. And at that address MNXYABCD, the statement we require is basically a jump ESP, because now what happens is the moment EIP executes this, EIP will point back to what ESP is pointing to and will start executing our payload. So basically the whole idea is we will now jump back to the stack indirectly by going ahead and using an address which contains an executable code which will force EIP to start executing from the stack, right? So how do we find this jump ESP instruction in the program's code? So in order to do that, what we will go is basically to the view tab and we will click on executable modules. Now we can take any one of these modules and search for the jump ESP instruction. So let's take the user32.dll which has been loaded. We can just double click it, and now the entire user32.dll code has been opened in our program. Then we can kind of right click and say search for command, and in that we can actually type in jump ESP. Right, so this is the command we need, and what we want to find out is a memory location which does not have a 0 in it as part of the address, but which will execute the command jump ESP. So let's click on find, and you notice we found an instruction located at memory location 7E429353, and this location contains the instruction jump ESP coded in the hex format FFE4, right? So this is the actual binary equivalent of the jump ESP command. So instead of using basically the top of the stack as the return address, we would actually use 7E429353 as the return address. So let's go back to our program, and now let's go ahead and remove this. Now, oops. What I'm going to do is, we know at this point we're going to override the return value after 268 bytes. So we're going to override this with the address from the user 32 DLL, and this address in reverse order is 5393.42.7e. So we have 5393.42.7e. Let me just verify that once again. 5393.42.7e, 5393.42.7e. Perfect. Right? After that, what we are going to have is the top of the stack ESP. Now here there's something interesting. Typically we can start our shellcode if we are very sure that this is the return address, or what we can actually do is create something called a nope sled. Now what is a nope sled? Well, if we go ahead and add the hex value 90 onto the stack, this 90 actually stands for the NOP operation or no operation. So when the CPU gets this instruction 0x90, it doesn't do anything, it just moves on to the next instruction. Right? So it's consuming CPU cycles, but basically the CPU is not doing anything, it's not using any of the registers, nothing. Right? So having the nope instruction does not change the program flow in any way, and what we are planning to do is actually have a small sled of nopes as they call it, and then below that we would have our shellcode. Now the reason for this is a lot of times when writing buffer overflows, we might not be able to pinpoint the location of ESP with a lot of certainty, and this may be true where the ESP top of the stack may differ even based on different service packs. So what we really want is that instead of actually pinpointing the exact address, maybe to have some buffer, so that even if ESP kind of goes ahead and points anywhere between that small buffer area which we've created, then it will actually hit some place in the nope sled and then go down, and our shellcode will execute. So in this example, we'll actually give 25 nopes, and after that we'll go ahead and add our shellcode. So don't worry if you've not understood the nope sled. We'll take up more examples in which we'll analyze why we need the nope sled and all of that in more detail. Just follow this for now. So this instruction basically stands for the NOP or no operation, which basically tells the CPU, well, just don't do anything. You wasted a CPU cycle, move on to the next instruction. Right? Okay, so after this we need shellcode. So let's go back, and we're going to run MSF payload just like before, but here's a difference. See, the problem is, if you kind of look at the payload generated by MSF payload, unfortunately it also contains the 0 value, and we know that if this goes through, then the input will be delimited after this and the rest of the shell code will not go through. Hence we require basically the payload to be devoid of 0x00 or any other bad character which the program cannot accept. So for this, instead of outputting this in C format, we'll output this in raw format, and then we are actually going to pipe this to MSF encode. Now MSF encode is going to encode the payload generated by MSF payload, and we can actually force it to actually remove the bad characters. So the architecture we are interested in is of course going to be the x86, and basically the bad character set is going to be a 0x00s, and after that the output format once again we require in the C array format. So let's run this. Awesome. Now if you kind of go ahead and look at the payload which has been generated, it does not contain any 0x00 value, right? This is just perfect. Let me just copy this, go back to the original program, and here let me just paste this payload. We don't really require the last 1800 bytes. Let's just remove that. Now one critical thing is also the allowable size of the payload, but we'll take that up in other videos, next video probably, right? Anyway, so coming back, first 268 bytes does not matter, just going to help us override the buffer. After that, we are pointing to a return address inside the user32 DLL, and this specific address contains an instruction called jump ESP, which basically will point the EIP to the ESP, which is starting after the next 4-byte boundary. And there we first have a nope sled, which basically doesn't do anything but provides some buffer region in case the ESP value differs a little bit here and there. And then after that we have our actual payload. So now let's go ahead and run this. The program is already running. Let's go back here, and what we notice is the program is still running, which, as we know from the previous video, is good news, because now we can actually connect to port number 4444 and look at what's happened. Awesome. So we have broken into the remote system, and a remote shell is currently running on port number 4444, and the program is also looking perfectly fine, up and running and working. So let's verify this even outside the debugger once. Right, the program terminated. If you notice, there was no crash. It terminated properly. Now let's go ahead and run the dev C++ code separately. Okay, so the program is running now all by itself, and we're going to run our code again. Program is still running, but the beauty is, as we know, we are into the system. Perfect. Right? So, well, what have we learned in this video? We've learned a couple of key concepts. The first is that, well, if you use functions like string copy which have delimiters such as null, then there are going to be bad characters which need to be found and eliminated. We've gone through the whole process of finding bad characters, and then after that, how to go ahead and remove the limitation if basically the ESP or any other address contains a 0 by finding a third-party DLL or probably one of the Windows DLL which the process has loaded, where we can have a jump to ESP instruction, and then using that we go ahead and exploit this vulnerability. Right? So that's all for this video. I hope you enjoyed this. What I would request is please download the program server-strcopy.exe. It's available with this video, and please try it out. And one word of caution, if you're using a different service pack, your offsets and all of that may come out differently. So please ensure that you follow the process, but don't use the code as is, right? Just verify the different values of the offsets, because even across service packs, user32.dll may have the jump ESP instruction located somewhere different. Okay? Hope you enjoyed. Please leave your comments behind. I always look forward to your comments and to learning more from you. Thank you. Bye-bye. See you in the next series. The next video, sorry.